I don't know how this happens every time, but I pause the recording. Never make your shortcut the space bar, because if you ever accidentally press it, it's going to just stop your recording. Yeah, so as we were saying, we have these three solutions here. We're looking at their conductivity, which one conducts electricity the best. And all we really need to look at, the number one thing for this example, is how many ions do you make? NaCl makes 2, MgO makes 2, CaCl2 makes 3. It has more ions, which allows more movement of charge to occur. It doesn't matter as much what their charges are. CaCl2 would be the greatest conductor of electricity. That's all that matters. If you get more advanced into like physics applications, the higher charges are going to increase it a little bit. So MgO would be slightly more conductive, we would expect, than NaCl, but you don't need to know that. So the only thing you're looking at for this sort of problem is just the number of ions it makes. All right. As we said before, some salts are completely soluble, meaning they'll break apart really easily, and some of them are not. Not all salts are soluble in water. There's a really complex set of rules that you can kind of memorize to help you more, but it's really all just trial and error. Some of them dissolve, some of them don't. To simplify it, we don't have to memorize that entire complex system. We memorize the same way I do for my honors chem, right? The 4 things, the positive or negative, anions or cations, that a salt can have that makes them soluble is sodium, potassium, nitrate, or ammonia. So Na, K, NO3, NH4. If something has one of those 4, we are going to assume it is always soluble in water, meaning it'll always break apart. And for our purposes, salts that don't have one of these 4, we're going to assume that they're probably solids. They don't break apart in water or break apart very little in water. Now, you've got all sorts of questions as we get more advanced here, where they'll tell you that this salt is soluble and it might not contain one of those 4 things, but that's okay, right? So this is the only ones you would be expected to assign their solubility to. If it contains one of these 4, assume it will break apart. It is aqueous. It will dissolve in water. And if it doesn't, and you have to make that assumption yourself, say that well, it must not, because it doesn't contain one of these 4. You can also not dissolve an infinite amount of salt in water. A completely saturated solution means it already has the maximum amount of salt or whatever else you're dissolving dissolved in it. So saturation is like your degree of how much stuff is in your water. You can't just keep pouring more and more salt. Eventually, it'll reach a maximum. And the more you add, it'll just stay as a solid at the bottom of your container. Now you kind of see this anytime that you add like salt to water. Like sometimes you might have a little like residual you can't quite get to dissolve at the bottom. That probably is because at your current temperature and at your current conditions, your water is saturated, has as much salt as it can hold. An unsaturated solution still has some room for more stuff. So if it's not saturated, we just call it unsaturated. Increasing the temperature, changing the pressure, doing a bunch of other things can make the things dissolve faster or be able to dissolve more. Okay, liquids experience intermolecular forces in much the same way that solids do. Liquid molecules are allowed to move around a bit in their containers, right? But they're held together as a liquid by intermolecular forces. So the thing stopping them from just floating away infinitely is their intermolecular forces. And you can even see this in like space, right? You see a little space video of people like drinking water in space. You just got like a little bubble floating around, a water droplet, right? But it's stuck together. It's not just going all these different ways. And that's because of the intermolecular forces holding that liquid together. Now, the stronger the intermolecular forces are in that liquid, the more energy you're going to need to break it, to boil it into a gas. Things with high intermolecular forces, as we know, have high melting and boiling points. They're more stuck together and harder. You need more energy to separate them apart. All right, here we have a couple different states of matter. It's kind of important to know these differences here. So solids, the molecules are pretty much stuck in place. They have a little bit of energy though, because all things above absolute 0 temperature have a little bit of energy. So these things are moving around. They're kind of wiggling in place, or vibrating or wiggling around, but they're not really moving anywhere. They're held in place by those really strong intermolecular forces, right? They don't have enough energy to even move, okay? Just to wiggle around. But applying more and more heat, warming it, or naturally reaching room temperature, or whatever's happening to it, will make it so that these molecules get more and more and more energy. And if they get enough energy, then they become a liquid. They have enough energy to not care about that they're being held in place. They have enough energy to kind of break that away. And that's what liquids are. Liquids are constantly moving past each other because at the temperature it's currently at, they have enough energy to outweigh the intermolecular forces trying to chain them in place. But the molecules are packed together still. They're still held together in groups, but they're kind of just like bouncing into each other, running around a little bit. They're still stuck as a liquid until they get enough energy to either boil, vaporize, or evaporate. All those things mean turning into a gas. And then once you're a gas, you're basically free to go anywhere. These gas molecules aren't going to stay in this beaker, right? They're going to go and fill up the entire room. If they get outside, they're going to just run into the entire atmosphere. Okay. So this is just kind of reiterating that. Solid particles hardly move. They vibrate in place. They don't have enough energy to overcome the intermolecular forces holding them in place. Liquid particles are free to move around and slide past other particles, but they are still stuck as liquids. They have enough energy to overcome the IMFs holding them in place, but they can't break out of their shape yet. They can't leave their general area. Think about it like a puddle, water droplet, or other body of water. The water is going to stay there. But gas particles have so much energy that they overcome all their intermolecular forces, pretty much. They can move independently in any direction and spread away from all the other particles. So it's important to kind of understand the particulate diagrams of solids, liquids, and gases, what their particles actually look like. And that leads us to kind of our last one here, which is vapor pressure. In any sample of liquid or gas, okay, anything where the particles are moving, they're moving around randomly. Right? They're not moving in a pattern, they're just bumping into each other, bumping all around, hitting each other, colliding head on, colliding head, like tail, like whatever, ramming into each other in all sorts of different ways. The speed of the particles in a sample always varies. Some particles are always moving faster than others by random chance, right? They happen to have more energy because they were collided into, right? Or they ran head first into the wall and lost most of their energy as friction, right? Some of them are moving faster than others. There's a distribution of velocities called the Maxwell-Boltzmann distribution that shows how many particles are moving at which speeds depending on the temperature. And to kind of look at that, we have a Maxwell-Boltzmann distribution, or three of them, here. So for whatever gas, this is for a gas, but same deal for liquids, right? For the red one, I have a 100 Kelvin temperature. And all my particles are moving between 0 and, maybe it kind of approaches it asymptotically, but most of them are moving less than 4,000 meters per second. My green gas, though, the temperature's higher. I have a large spread of how fast they're moving. It starts at 0 still, right? But it's moving all the way up to like 6,000-ish, right? So some of my particles are hardly moving at all. Some of them are moving really, really fast. There's a huge distribution of how fast they're moving. The temperature is kind of the average energy. So kind of the average, the mean that you would find in this curve defines your like temperature. And then this blue one, they're 1,000 Kelvin. So they're super hot. And they're starting either at 0 or going all the way up to way off this scale, maybe to 12,000 or something like that. Right? And because of that, it's kind of important to know that not every particle in a sample is the same. Some of them are moving way faster and have way more energy. What that means is that if you have a liquid, right, the particles in that liquid, some of them are moving really fast, some of them are moving really slow. Now, the ones moving slow don't have enough energy to do much. But the fastest few particles are moving fast enough they turn into gases. They have enough energy to escape the liquid phase and turn into gases. Here I have a sealed container that initially contained like no air, right? But there's a little bit of vapor in here, right? So whatever this is a water molecule, right? So whichever ones are moving fastest by random chance will turn into gases because those fast molecules have enough energy to overcome the intermolecular forces holding them in the liquid phase. And they turn into the gas phase. And then once some of the gases slow down, they turn back into the liquid phase. And this cycle happens all the time. And this will happen with any sort of liquid. If you have a bottle of soda, you have a little bit of gap at the top of that bottle of soda. That's actually full of vapor. And that's part of the reason that when you open it for the very first time, right, it releases like some pressure. That vapor pressure is being released. The amount of gas molecules created is called vapor pressure. So some molecules, or some samples will be really volatile and have a lot of vapors. Some of them won't have that many at all. And it has to do again with intermolecular forces. Liquids with the really high intermolecular forces, think about them. They're very strong. You need a lot of energy to overcome those intermolecular forces. And because of that, they make less vapors. They have a lower vapor pressure. So if you have a high intermolecular force, your vapor pressure is low because you're not making very much vapor. Only the very, very top percentage, like millionth of a percentage of your particles have enough energy to escape the liquid phase to turn into a gas. It still happens, but much less rate. So things like water have very low vapor pressure. So if you just have a water bottle and you open it, it's not going to make much vapor. Now, liquids with low intermolecular forces, things that more easily turn into gases, will have a much higher vapor pressure because they just have a lot more particles that have enough energy to escape those intermolecular forces. Because there's less force holding the molecules in the liquid phase, it's easier to escape into the gas phase, and so a higher percentage of particles are in the gas phase, meaning there's more pressure. So an example will look like this. Which of the following liquids has the highest vapor pressure? So I'm just going to take a look at all of my different liquids here. H2O, HCN, C2H6. All right, so I'm looking for the highest vapor pressure, which is backwards. I need the one with the lowest intermolecular force. You can kind of think about it, you got a bottle, and you have some liquid in here. Right, something with really low intermolecular forces will be a liquid still, okay? But it's going to be easier for the particles to escape. So there'll be a whole lot of the liquid particles are moving fast enough to turn into gases. And if you have that same liquid, or not that same liquid, but that same container, yeah, this is the exact identical container, by the way. But this liquid has high intermolecular forces. Some of the particles will have enough energy to escape, but maybe only like a couple. Because of that, this one has a high vapor pressure because there's a lot more vapor. This one has a low vapor pressure. This is the only relationship with IMFs that's like backwards. Usually high IMF is high boiling point or high anything else. But this is the one relationship that's backwards, which is why they love to ask it. Low intermolecular forces make your vapor pressure higher. So if we're comparing these, this one has I'm just going to start and just tell you guys know. This has hydrogen bonds. So it has the highest intermolecular forces. C2H6 over here has London dispersion forces, but it doesn't have dipole forces. It's nonpolar. And it doesn't have hydrogen bonds because it doesn't have a hydrogen bonded to an N, O, or F. Now I have HCN here, I'm not sure about. I know it has London dispersion forces too, but if I draw it, the CH part is nonpolar, but the CN bond is polar. So this has dipole forces also. Okay. So H2O has all the types. HCN has London dispersion forces and dipole. LDF's only in C2H6. So this has the lowest, so it is your answer. It has your highest vapor pressure. That liquid would make the most vapors in its bottle. All right, and last today we have chromatography, which we'll do a lab on this in class, but chromatography is the process used to separate mixtures based on their polarity. And it uses the same idea of polar things dissolving other polar things, and polar things not being as good at dissolving nonpolar things, to separate stuff by their polarities. And we'll talk about how we do that. Chromatography's main purpose is to separate dyes and pigments, because chroma means color. So you're usually separating things into like all their different colors. Here's a bunch of different types, and you see the colors kind of coming into play. Chromatography is used in all sorts of analytical laboratories and stuff. I've used a handful of these. I've used paper or HPLC or gas or thin layer. So these are all things that you would do in like a college chemistry class. It's just like gas chromatography is like really expensive and stuff like that because you need like helium gas and some other stuff. We're going to use the one that looks the lamest because we don't have any money. We have paper. So we're going to do some paper chromatography together. You can still kind of see the effects on paper. It's actually the easiest one to do math with and the easiest one to kind of do models of. So like there's a lot of benefits of it. But some of these other ones are a little bit more sophisticated, of course. So paper chromatography is what we're going to use in class. It's also the only one you see on the exam. Now it has a thin sheet of filter paper. And that filter paper here is hung up in some sort of container. We'd probably use a beaker, but whatever, this is a fancier container. And it's dipped into some solvent here at the bottom. Okay. The thin sheet of paper is called the stationary phase because it is not moving. Right? The wording phase makes it sound fancy, but it's just piece of paper is the stationary phase. Way to think about it, you always also call paper stationary, right? If you're doing like crafts, so like stationary phase, paper phase. But it's called that because it's not moving. Now the thin sheet is submerged in a shallow pool of solvent. A lot of the time we'll use water, but you can use other solvents as well. The solvent will move up the paper due to capillary action. Like a straw, the paper will just get soaked with a little bit of water, and the water will slowly move up the container. Therefore, the solvent is actually moving, and we call it the mobile phase because it's moving. It moves through the moves through the paper. All right, you place a dot of sample you want to know about on the starting line. Now, that starting line is above the water, so it's not dissolving in the water, right? But as the solvent starts to go up the paper, it will dissolve some of this dye and pull it up the paper with it. As the paper absorbs water, the sample will begin to move and separate into its components. Some colors are made of several different dyes that have different properties. Now, the dyes that move the farthest, the reason they're moving is because they're attracted to the water that's moving up the paper. So in our example here, right, we have water as our solvent, which is polar. So the dyes that move up the most are the ones that are the most polar. The polar ones are attracted to the polar water. So like in our example here, this orange color that goes up the highest in both of these examples is probably the most polar dye we have because it traveled furthest up the paper. This blue dye you see over here wasn't as polar. It still traveled up the paper a little bit. It was slightly attracted to the water, but not nearly as much. Because of that, it doesn't physically travel up the paper as much. So the one that moved up the most is the most polar. The one that moved the least is the least polar because it's most attracted to the paper and less attracted to the solvent. Now this all flips around if you use a non-polar solvent in a polar piece of paper, but that's a really rare example. But pay attention to your phases. So your mobile phase, the one that's moving, is if the dyes move with it, that means they're attracted to it. So if your mobile phase is nonpolar, that means they're nonpolar because nonpolar things are attracted to nonpolar things, right? If your mobile phase is polar, the things that move with it most are the most polar because they're the most attracted to it. So whichever things move the most with your solvent are most attracted to it. In paper chromatography, the paper is usually nonpolar and the solvent is usually polar, but you can flip it around. The more polar dyes are more easily dissolved by the polar water and move up the paper with it. The less polar or completely nonpolar dyes are not dissolved well by the water and tend to stick to the nonpolar paper, meaning they'll move less. Like attracts like. Polar things attract and dissolve polar things. Polar things are not great at dissolving nonpolar things. Nonpolar things attract and dissolve nonpolar things. We can also do a little bit of math to analyze it. We can analyze the separation quantitatively by calculating RF values. The RF value tells you the ratio of how high your sample traveled compared to your solvent. Okay, so this is a very simple sort of way to calculate. It's basically, okay, A tells you how high your water moved, and you would mark that physically with a pencil. B tells you how far your dye moved, and you'll mark it to the middle of that color, right? So that's the most concentrated part. And then all you do is take B, the distance that the dye went, divided by A, the distance the water went, and it just gives you a ratio of how high your dye went up the paper. Okay? So like B here, it looks like it's about 75%. So its RF would be about 0.75. Blue has an RF of about 0.5, maybe a little bit above. Red's RF would be about 0.8, right? It's about 80% of the paper, and so on. So it's just a way to calculate that. And the reason we have that, especially when you have more sophisticated types of polarity, you can get these numbers really, or more sophisticated types of chromatography, you can get these numbers really accurate, right? And you can use this to test what sort of dyes are present in a mixture. The RF values of dyes or pigments are recorded and can be used to analyze an unknown sample. So over here, I have some examples of different types of chlorophyll, right? We have chlorophyll A, chlorophyll B, carotene. Is this something, lutein, whatever? Right? You have these different things and they have a literature RF value, meaning this is what their RF should be expected to be. And whatever experiment this was, you can see that these numbers pretty much match with what their expected RFs are. Now we're going to use this because we're going to use like different colored like food dyes. And you might notice if you know anything about food dyes, there's a bunch of different numbers like a red 40 or red 6. There's actually different red dyes that turn in different colors. And some of them have different RF values. So if you have a red dye and you don't know what type it is, you can try to guess based off its calculated RF value. You can compare it to a data table you can find online. Okay? So that's kind of the purpose of chromatography. You separate things on a piece of paper to see how far they travel. You can compare that to some reference values to kind of analyze what an unknown dye might be. All right, and that is the end of this section. Sorry for splitting it into two, not intentional. Okay, so we talked about all sorts of different things about intermolecular forces of liquids. We talked about a lot about solubility, what dissolves in what, and we ended with some chromatography. All right, hope you learned something, and I'll see you all soon.